So we're going to consider motion in two dimensions, and you will want to recall the stuff that we did when we described the motion in one dimension. Remember, we used vector quantities, and to show the direction, it was just possible to use just positive or negative in that case, since we only really had one direction. But now we're going to have two directions, the x and the y. We're going to use vectors. We're going to split the components into their x and y components for each vector. And so it's insufficient to just have positive and negative, okay? So we're still going to be interested in the same quantities we used to describe one-dimensional motion, if you remember that. Those quantities were displacement, velocity, and acceleration. So let's look at these in two dimensions. Displacement first. This is my space in which the motion is happening. So here is the origin, here's my coordinate system, x-axis and y-axis. And the object moves along this dashed line. So it's a curve that the actual path of the object takes. We're going to consider two positions, a starting position, which is an initial position, and a final position. So on this curve, let this be my initial position at some time initial time ti, and this is position p, and a final position at time tf, marked as q. So the initial position we can define with a position vector in polar coordinates. The position vector would be ri, okay, from the origin to that point p. Similarly, the final position vector would be rf, yeah? And so the displacement would be the final minus the initial. So delta r is my displacement, which is rf minus ri. And that's the formula here. Delta r, which is a vector quantity, is rf minus ri. This is a vector equation, okay? You cannot do a simple subtraction, okay? Remember the vector subtraction that we learned. So since the units of both these position vectors would be in meters in SI units, so delta R will also be given in meters. Okay. Now let's consider velocity. Velocity, if you remember, is the rate of change of displacement. That means delta R here, which is the displacement, divided by delta T. This is going to give me my average velocity. By definition, these three lines means by definition. If I want to know the instantaneous velocity, I need to take this, and in the limit, delta t tends to 0. Yeah? You will not be asked to calculate that mathematically, but you should understand that graphically that represents the tangent at the given point, okay, that we're talking about, the given instant in time. And its units is then going to be meters divided by unit for time, so seconds, meters per second. What about acceleration? Acceleration is the rate of change of velocity with time. So we have meters per second, or meters per second squared. Okay? This defines our average acceleration. And similar to velocity, if we want instantaneous acceleration, we need to take this formula in the limit delta t tends to 0, or the tangent to the velocity time graph, okay, at a given time. So these are my new definitions of the vectors. And just to summarize them, displacement, average velocity and instantaneous velocity, average and instantaneous acceleration, and the units are meters, meters per second squared, okay, correspondingly. So a little more about acceleration, because this is important to understand. Acceleration being a vector quantity, that means it has magnitude and direction, being defined as the rate of change of velocity. Yeah? So if the velocity changes magnitude, clearly there's an acceleration. See, I'm going at 30 miles per second, and then I change to, let's say 30 miles per hour, and then I change to 50 miles per hour. I have clearly accelerated. Yeah, the magnitude has changed. We're familiar with that. But if I stay at 30 miles per hour, and I go around a curve at 30 miles per hour, then my direction of velocity is changing, but the magnitude is not changing. Okay, so the speed remains constant, just the direction changes. That is sufficient change in velocity to create an acceleration. Okay, so we may have an acceleration without a change in speed. That's important to understand. And of course, you can have a change in both direction and magnitude. So as I take the curve, I could be changing direction and also maybe lowering my speed down to 15 miles per hour.